Hello guys, a very happy morning to every one of you. And guys, now we are just going to start our next classes. Especially this is called bending stresses in beam. So now we are just going to see the extra detailing thing about the bending stresses in beam. So why this bending stresses in beam? It means in this chapter I'm just going to explain each and every detail. So okay. So I think so without wasting time, let us get started. So just what is stress? Stress is force per unit area. Suppose if bending means, for example, this is the pen. Suppose if we just bend it means for this also the bending stresses will be okay. This is just a simple thing. It's called as bending stress. Okay. Just 1 second. So I think so you can see this one. So bending stresses in beam. So the main Euler's-Bernoulli equation, you can see bending stress formula is this: sigma y divided by mi divided by LCA. Okay. Or for just a simple sake, you can see Elizabeth Rani, may I help you? That's it. Okay. This is the basic formula, and you can see this bending stress. This is the it means the distance. Okay, not deflection. This is bending moment. Okay. This is inertia. This is radius. This is Young's modulus. Okay. I think so you can understand. So if they ask the bending stress means sigma equal to my divided by I. Okay, that's it. So you can see 1 by r. So each and everything. So for this proof is not there, because if proof we just given means it goes to bigger things. So that's why. Okay. So you can see this one. So simple thing. If it given me what is the bending stress, m equal to minus p of x. Okay. Put here, and distance will be mostly, guys. For example, distance will be like this, means we need to take the neutral point. After we need to go to the top section. Okay. I think so this will be the y. Okay. So after going to the in detail section, I'll just explain you. Okay. So don't need to worry. So next thing you can see bending stresses P. So just a simple thing. If you don't know bending moment means dash shear force. So this is P by 2. This is L means L by 2. So P L divided by 4 is the bending moment. Okay. So if it's been given like this means, so how it will be like this. Okay. You can see this is the midpoint. So this is definitely L by 2. And this is what will be the reaction will be. You need to calculate. So I think you can understand. So definitely for this W L squared will be 8 will be the bending moment. Okay. So sometimes we need to calculate, sometimes we need to just go according to it. Okay. So next you can see about this one. So for this the bending moment will be W L squared divided by 12. Okay. So the same thing for this bending moment will be W L squared divided by 2. Okay. At least you got the point. So where the bending moment is maximum, there the shear force will be definitely 0. Okay. So now we can just go for the critical section. This is what I just tried to explain to you. Critical section. Critical section where bending moment is maximum. Okay. Where bending moment is maximum. Okay. It is called as critical section. Suppose you can see, for example, this is height, this is breadth, and you can see what is the inertia of x-axis equal to b h cube divided by 12. So you can see about this one. Okay. Whenever you just putting the inertia will come. Okay. So in here you can see this the stress will be lesser, but while you go upper, the stress will just keep on increasing. So at this section, this is a critical vapor. At this section, the stress will be maximum of the limit. Okay. So you can see the distance we are just going upward. This is called y. Okay. We no need to take the entire axis of h. We are taking the neutral axis from there. We are going upwards. That's it. So okay, I think so you can understand. So where is the time? So you can see. So whenever you just go, only 10 millimeter. It means 10 millimeter means, for example, this is the neutral axis, we are just going 10 millimeter. This is 20 millimeter. This is 50 millimeter. So 20 millimeter means you can see the stress is only 5000 megapascal. Whenever you go 20 milli, it means millimeter above, you can see 10,000 megapascal is there. So I think so got the point. So critical section, at which the section there is a maximum bending moment. Critical fiber farthest from the neutral axis, where bending moment occurs. Okay, for critical fiber, the critical section should occur. Critical section का critical fiber, if failure doesn't happen, yes, if the failure doesn't happen, then our beam is safe. Okay, so next one, moment and IEC are same, and first we need to select the required. This is a normal thing. Okay, first we need to find the neutral axis. After finding the neutral axis only, we need to measure the fiber. Okay, I think so got the point. So next thing you can just see. So you can see representation of the bending moment stresses. Okay, you can see generally where the bending moment is so much high, that there will be the critical stress and critical each and everything. So you can see, suppose we're just giving this, what will happen? You can see definitely it will bend like this. You can see definitely it will bend like this. Okay, so you can see here the atoms are being placed, means you can see here the atoms will be expand. So but here the atoms will be compressed, so much gap will be so much here. So upper portion will be compression, bottom portion will be tension. Okay, I think so you understand. This is the neutral axis and each and everything is given. So this is 3D format. For example, if like this neutral axis means, so upper portion will be compression like this, so like this. So bottom portion will be expansion, going outside. So you can see about this one. So like this, definitely it will be like this. Okay, just a normal representation. So it will be compression till now. Here it will be expansion. Okay, tension. So you can see how much a bigger is the thing. I think so got the point. So next one, you can see if y equal to 0, in which definitely they will just give the 100 millimeter different like this, and they will calculate the sigma b. So guys, generally at a neutral axis, bending stress will be 0. Okay, bending stress will be definitely 0. And you can see in above example, if the fiber is 40 mm bro, okay, this is a normal thing, you can definitely calculate. So we can just see a question. This is the question. P, and this is the critical sections. Okay, so just expand it here. So definitely they would have given the question. So neutral axis, so you can see y equal to, so this is y, this is entirely is h, so this is h by 2. Okay, y equal to h by 2. It means from this is the entire thing is 0 like that, we need to consider, we need to go up like that. Okay, so what they have just asked, they just asked what is the height. Okay, so sigma equal to mi divided by y. So bending stress, whether they have given, yes, bending stress they have just given at the critical fiber 100 to 10 power 6. What is the moment given? 12,000. So what is the inertia into oh, that's the thing is called as 12,000. Okay, moment is moment, you can say for this one. This entire thing is given, and 1.2 into h divided by 2 divided by h divided by 2. Inertia is for this moment inertia only we need to take. Okay, do not confuse this entire moment of inertia, this small moment of inertia, h by 2 into h cube divided by 12. Okay, now we just cancel, we can just find it easily. Okay, next let us go to put this question. So you can see the bending stress will definitely like this 12, and now it will be like this, and 12, this or 12. So here you can see 12, this is 5, 12 means you can see the entire thing you can just calculate. This will be more than 12, and you can see like this, it will go on like this. Okay, so this entire bending moment, okay. So this you can see it means bending moment equal to like this. So two rectangles are there, first rectangle plus the second rectangle. Just add and you can just proceed, okay. So just normal thing guys, no need to confuse yourself. So next one you can see where they just asked the load, okay. What is the load? Suppose if they are given like this P. So each and everything is given, bending stress given, inertia is given, distance y is given, each and everything is given. They are just calculating the load, okay. What is the load? Okay. So next one, cylinder. Oh wow. So you can see they are applying the load here, okay. So moment, it's just guys, you can see it is a cantilever with a different structure. That's it. 1 max equal to P into L, okay. So load definitely they would have given, and sigma equal to my divided by Fi, okay. So what is the inertia of a cylinder? I equal to pi divided by 64 d power 4 minus d power 4, okay. Inertia equal to pi by 64 d power 4 minus of d power 4, okay. So bending stress equal to 50 into 10 power 6 equal to moment m into inertia is d by 2, okay. So just take the distance. So this entire thing is d, and you can see what is this one, d divided by 2, okay. D divided by 2 pi by 64 d power 4 minus d power 4, okay. So now you can calculate each and everything, okay. So next thing, load given, now the deflection is 5 millimeter. What they are asking, they are asking to calculate A, I think so, okay. Load they have been given. So but the deflection, okay, you can see cantilever again, deflection equal to P L power L cube by 3 EI, okay. Now based upon this you can definitely calculate the P, okay. Oh, I think that they are asked about P, okay. They are asking about load. So deflection we know, and it's been given EI and L we know. So each and everything you just put, and you can just directly get the answer. So you can see definitely guys, it's such a simple thing only. However, the neutral axis, in the neutral axis definitely the bending stress will be 0, okay. Okay. So you can see definitely the neutral axis here, the bending stress will be 0, and you can see here bending stress is 0, but while you are just increasing, while you are just going upper, the bending stress will be maximum like this, okay. Here the bending stress is maximum. Why? Just a simple thing, as you can see, while we are just going upper, what is happening? The distance is reducing. For example, you can see the distance, see here you can see only point is there. So in this point the bending moment will be so much higher, okay. I think so I got, sorry, the bending stress will be so much higher, okay. I think so I got the point. So just a normal thing for each and everything like this. So okay. So suppose you will just take for the I, for I also it will be same like this. Okay. All we see is symmetrical section. Okay. So bending stress you can see this one. Oh yes, definitely for triangle you can see. For each and everything you have to just go for the centroid. From centroid you can see above this one. So you can see here the bending stress will be maximum. Here the bending stress will be minimum. Okay. Maximum area only we need to take. Okay. For example, if how to say means if like this the area given, so first we need to find the centroid. After finding the centroid we need to go to find the distance. So you can see this is the bending stress. Here will be maximum, here the bending stress will be minimum. Okay, because you can see the area and you can see this is the area. Where the area is minimum, there the bending stress will be maximum. That we need to take. Okay, so for this one you can see, so you can see first we need to find the centroid. So after finding the centroid, you can see here definitely the bending stress will be minimum. Okay, here the bending stress will be maximum. Okay, I think so I got the point. So you can see the value of each and everything. I think so you can know. So this is a normal thing, you can definitely do it. Okay, definitely find it. Okay, so this one 100 minus f x, this one x. Okay, 200 divided by x, 100 minus f x divided by 800. So after calculating next we can just find it. Okay, so this one you can definitely do it. So you can see about this one, if they have given like this means simple. Elizabeth Rani, may I help you? Okay, so sigma y divided by Elizabeth Rani. Okay, sigma equal to ey divided by fr. Okay, okay, I think so I got the point. Okay, so next thing it is, okay, so critical fiber you can see bending moment maximum, y maximum, that stress will be maximum. Okay, each and everything maximum you just put. So next thing is, if you just taken I divided by y max. Okay, it is called as z. That is polar moment of inertia. Okay, so I think so you can see, so if z is, suppose you can see sigma equal to moment divided by z. You can see if polar moment of inertia is so much high, the stress will be so much lesser. Okay, z higher, the stress will be lesser. If polar moment of inertia is lesser, the stress will be higher. Okay, I think so again. So if stress is lesser means here the area will be good. Okay, the area might be maximum, here the area will be minimum. Okay, so you can see that denotes the strength of beam in the bending. Okay, that must be high, and jitna okay this one. And the next best, one of the best section is I sections. Okay, I section, one of the best section that you just wanted to know. Suppose you can see there are a lot of railway tracks, it will be mostly of I section because it is the best section. You can see because most of the area is away. Yes, definitely guys, other one thing is, whenever area is away from the neutral axis, it is the best. Okay, it is best. And why I section means, for this section more or less is the best thing. Okay, I think so you can see this diagram. So I is the best. This one like this, and different, okay, different thing we are just placing like this one and like this one like that. Okay, I think so you got the point. So you can see all beams have same cross sectional, and this one metal. Okay, I section, this one concrete. So metal is section is generally a best thing. Okay, so the next thing you can see here, the diameter, it means okay, so you can see we have just taken 3 types of wooden logs. So in this, which one you need to do? For example, I'll just show three different thing. Okay, so first I'm just taking the box like this, and next I'm taking the box like this. Okay, next I'm taking the general thing like this. Okay, so but the diameter is same. Okay, diameter same. Diameter same. Okay, so you can see diameter is always fixed and sides matching, breadth and height is different. Breadth, height is changing, breadth, height is and everything is changing. Okay, so I'm just taking a normal thing. This is diameter, this is height, this is breadth. Okay, so that equal to I maximum divided by y of maximum. Okay, what is that? H b cube b h cube divided by 12 divided by y is h by 2, so that is b h square divided by 6. Okay, you can see the polar moment of inertia depends on breadth as well as the height. Okay, and the polar moment of inertia is not a normal thing. You can see it is square, so it is parabolic. Okay, just one second. And we definitely need to make that into single variable. Okay, now we can just do it's only breadth height, so Pythagoras theorem, d equal to b square plus of h square. Okay, so h square equal to d square minus of b square. Okay, that equal to b by 6 d square minus of b square. Okay, so you can see now also two variables, so we need to differentiate according with the b. Okay, so dz by db. Okay, equal to what will come? So d square b minus of d cube 1 by 6. Okay, this one we just differentiate. Okay, so 1 by 6 d square minus of 3b the whole square, this will come. So for maximum minimum put this equal to 0, so d square equal to minus of 3b square equal to 0. Okay, d square equal to 3b square. Okay, diameter equal to root of 3b square, d equal to diameter equal to root of 3, or b equal to d divided by root of 3. Okay, this is the minimum. Whenever you just take the breadth in this direction, we will get the maximum usage of material. Okay, so now we have to find the height. Okay, h equal to d square minus of b square. So now we just go and put the b equal to d divided by root 3 here, and we can calculate the height. Okay, so it means for best beam should be means breadth equal to d divided by root 3, height equal to 2 divided by 3 of d. Okay, I think so you are getting the point. Okay, so you can see they have just given the polar moment of inertia of rectangle and polar moment of inertia of circle is equal. So according to that, we just calculate in this script, and as well as the weight of the weight of rectangle with the weight of circle. I just can just calculate. So this one I will just tell in the problems. Okay, so next one is combined load. This one is P, and okay, you can see whenever the thing is being like that, you can see definitely here which means until the x only we need to take. Okay, this one suppose is L means this one is x. So suppose you can say, I think so you can understand this small length, it means L by 2, so x plus of L by 2. So here the definitely, so here the p will be as well as the p L by 2 plus of x will be. Okay, I think so you got the point. So here the combined load, you can see axial load is also there, and as well as the bending moment is also there. Okay, you can see some attachment you apply and apply the load again, definitely it will look like this. Like this, as well as the bending one like this. Okay, you can see this is the axial stress, this one is the bending stress. Okay, I think so I got the point. So bending stress will be my divided by a. Okay, yes. Okay, I think so I can understand sigma of a be equal to direct stress plus of bending p by a plus of my divided by. Okay, so this side you can see here it is going downward, but here it is going, one side is bending stress going up. So you can see direct stress minus of my by 5. Okay, you can see about that. So in the neutral axis, definitely as guys here there is, you can see this is neutral axis. Okay, for example, if you just take like this, you can see this is the neutral axis. So you can see here the neutral axis, even though in the neutral axis the bending, it means the bending moving stress is 0, the normal stress is not 0. Okay, so you can see this one. So this is just a problem, I think so I can equal, and I will just definitely explain it later on. Okay, these are the other thing has been given. So you can see whenever it's been applied given like here, and you can see mostly in the strength of material we need to apply in the middle section. Okay, so you need to just place this p in a middle section like this. Okay, and you can see this combine, and we will just create this load, and this combine. So I'll just definitely fill in the, it means whenever the problem comes I'll just definitely tell this one. Okay, so guys, the next thing is called the strain energy method. Okay, you can see this is strain energy method. So this is stress and this is so entire things. Okay, you can see this is E. It means E means what? Strain. Okay, the stress. Okay, so you can see a body will have infinite point of resilience. Resilience means just you can see strain energy absorbed by the body within elastic limit. So if this is elastic limit, within the elastic limit, how much the strain energy is stored, that's called as resilience. Okay, proof reliance is up to, it means the maximum limit. Okay, so you can see this is the maximum limit of elastic limit, but resilience means up to only here, up to here only we just given the strain energy, means up to this we are taking. Suppose if a maximum means, you can see strain energy absorbed by the body up to a maximum of the elastic limit. So this is proof reliance. Okay, I think so you can understand. So you can see within is this one, so up to is you can see directly 100. Okay, suppose if it's given 99.9 also it is within. Okay, and you can see material steel, and so you can see here the, suppose you can say guys, for each and everything the material depends on the material, the absorbing capacity is so much difference. Okay, for example, if I take this pen and I just give a like force like this, means you can see the stress is being absorbed fully. But if I just cut the pen into half, and if I just give the stress here, you can see the load can be taken. If the load here, the energy absorbed will be maximum, but here the energy load will be applied to the minimum because it is dissipated. So you can see for this proof resilience will be 100 joules. For this you can see smaller thing, it will be different. All object differs, volume also differs, but only the proof reliance also differs. Okay, but the main thing is proof reliance is not a material property. Okay, how we can just calculate, you can see modulus of resilience equal to proof resilience divided by volume. Okay, so now the modulus of resilience will be same for all the, yes, definitely divide the thing with respect to the volume. Okay, so you can see 100 divided by the volume is 2, you can see 150, 750 divided by 1.5, so you can see it is 50, 50 divided by 1, it is 50, and you can see proof reliance may differ, but moment of modulus of reliance will not change. Okay, so I think so you can understand. So you can see modulus of resilience is a material property. Okay, modulus of resilience is a material property. Modulus of resilience up to divided by volume. Okay, I think so you can understand. So all within the elastic limit. Okay, toughness. What is toughness? Energy absorbing capacity of a body up to fracture. Okay, energy absorbing capacity of a body up to fracture. It means up to the fracture. So you can see material same this one, and but you can see volume depends. Okay, so for this one the volume will be more. For this one the volume will be lesser. Okay, this one 1000 joules, this one 100 joules, more energy to take and less energy to take. Okay, so modulus of toughness is toughness divided by volume. Okay, so modulus of toughness is equal to toughness divided by volume. So कोई body को proof solution. Okay, so toughness of a gas is very low, yes definitely, but for the glass it is hardness is so much high. Okay, it means for most of the glass you can see, and the other thing is called toughened glass is also been there. Okay, laminated glass, so glass will be plastic, glass plastic like that. Okay, so you can see the bulletproof proof glass. Okay, this one toughened glass and plastic toughened material also is there, and hardness and surface indentation and modulus of resilience equal to the entire thing 1 by 2 sigma of E. Okay, so modulus of resilience you can understand. So this is a thing to calculate other thing. For stress and E we need to put here, and you can see P square, this one P square divided by 2 A square of E. Okay, so if it is given resilience is proof resilience modulus of resilience into volume, so modulus of resilience 1 by 2 sigma into E into volume. Okay, and the volume is A into, so the entire thing is P square divided by 2 times of E. Okay guys, just remember this one, because while the problem is coming I'll just explain each and everything. Next one, modulus of the 1 by 2 sigma of E. Okay, so you can see sigma E, so this one put here sigma divided by E, and you can calculate modulus of sigma square divided by 2 times of E. So modulus of resilience is directly proportional to sigma square, it is parabolic. Okay, the same thing goes for the E also. E equal to stress divided by Young's modulus, the same thing goes for parabolic. Okay, modulus of resilience centrally parabolic to the stress and strain. Okay, I think so you can understand. So this one I'll just explain it better. In cash loan theorem we don't take axial load. Okay, so while the problem is coming I'll just definitely explain you. Okay, so guys, then let me see the next one, and then take care. Bye bye, have a good day.